Hi everyone and welcome to a new video about digital controller design. This is our example number 3. In this example we will discuss the PD controller design in the digital domain. We will work out our calculations step by step and also verify these in MATLAB simulations. So let's look at our situation. We want to design a digital PD controller such that the settling time is less than 0.4 seconds and there is also an overshoot specification must be less than 12%. And our sampling period is 0.05 seconds or 50 milliseconds. And the system is shown here. So we have a plant. And again, as said in the previous two examples, we have a hold here to hold the sample. In order to hold also the sample at the input and also sample at the output, we also have a sampling here, which is then in between there is also the controller PD controller. The plant here, which is given by G sub P, is given by this expression, which is a second order system. So how can we design now this digital PD controller for these two specifications? So let's look at it step by step. We start first with the design point in the S domain. So that is given by the real and imaginary value in the S plane, which is the sigma d and the omega d. Now from the specifications, first with the settling time, real value, we can determine how we can use this settling time for this sigma d. Settling time specification for 2% is 0.4, and we know settling time is given by 4 over the sigma d. So the sigma d itself is then 4 over that settling time. So we have then 4 over 0.4, that must be then 10. So our sigma d, our real value, must be then 10, of course here minus 10 later. The imaginary value, omega d, can be determined using the overshoot specification. Now we know the MP, which is the overshoot itself, and the scalar value is 0.12. When you convert that to the damping ratio as a pure second order system, you can use this formula, and the zeta is our damping ratio. And when you now do the calculation here, you get 0.56, very close to that value. Now we need to determine omega d. Now there's a formula for that in order to calculate directly the omega d. This is the angle which you first determine, which is the arc cosine of that zeta. And then you take the tangent of that angle times the real value, which is 10, give you directly the omega d. This is just geometry in the S-plane. And when you do that, 10 times the tangent of the arc cosine of 0.56, you will get 14.8. Now we also have our imaginary part. So together we have our design point in the S domain, which is the minus 10 plus J 14.8. Okay, we now move on and then convert our design point from the S domain to the Z domain in order to determine the controller in the Z domain. So for that we use the exact transformation from the S plane to the Z plane, which is defined by this expression, which is then S is equal to e to the power st. I have discussed in the previous videos, in the first example, specifically about the P controller design, that you can use a Tusting approximation or Tusting transformation when the calculations can be a little bit tedious, and that is one of the reasons I discussed here. And then here I will just use this directly in order to see also difference between those two methods. So we use directly the z is equal to e to the power st. In this case, the s is our design point in the S domain, and the Zm will be our design point in the Z domain. So we will just substitute the Sm and also the T, which is our sampling period, which is 0.05. So when you do that, you get this expression. You see that this is the design point in the S plane, and this is our sampling period. You can now work out the parentheses. You will have this expression. Now you can use the property of the exponents. You can now split this by multiplying two exponents. So you get e to the power minus 0.5 times e to the power j 0.74. Now this is just a number, also let's say the magnitude of that expression, and this is the angle given in radians. Remember, it's not degrees. So we can now determine that just as a value, which is approximately, of course, 0.6065. And here, this part, we can use Euler's identity in order to get the real and imaginary value. And again, remember that 0.74 is in radians. Now, when you do that, calculate that, or first also multiply out the parentheses. And when you do that, you will get 0.448 as the real value and 0.409 as the imaginary value. Now we have our design point also in the Z domain. Now, next step is also determining the hold operation here. That is a transfer function given here in the Laplace domain, which can be proved, and this is the result. And so we will need to use this in order to get to the complete Z transform of the plant itself. Because Z transform of the plant itself is composed of the sampling, holding, and the plant itself in the S domain. So together, that is then, this is by the way the zero over hold as said before, so the sampling, hold, and the plant transfer function together is given by this expression. So the hold transfer function times the plant transfer function, both in the S domain. Now when you just multiply them together, you have this, and you can also write it down in this format, so you move this S in the denominators. You have now here this expression. Now we need to take the Z transform of this expression. So the Z transform of the sample, hold, and the plant transfer function, that's the next step. So G of Z is equal to the Z transform of this expression, which is then the Z transform of this expression. But we know the following situation. We know Z is equal to e to the power st. So e to the power minus st is, this part here is only Z to the power minus 1. So we can take it out, and that will be then also easier to calculate the Z transform. So let's take this out and also make that directly Z to the power minus 1, and then only take the Z transform of this 50 over the S times S plus 10 times S plus 15. Now this is easily done using partial fraction expansion in the Laplace domain, of course, first, and then you need to look at the Z transform table going from the Laplace domain to the Z domain in order to calculate also the required Z transform of this one. So that is, there are a couple of steps in between. I just skip those steps and give you directly the result, and this is the result for the G of Z, which is our Z transform of our plant as said, including the hold and the sampling. So we are now done for this step. Now moving on and looking now at the next step, which is our controller transfer function. We need to have a PD controller. That's specifically for this example, and the PD controller is composed as the gain and also the derivative part, as said also in the root locus analysis for analog controllers. We have the K1, that's just the gain, and the K2 times the derivative action. Now we can now take this together in one fraction. First write this down in K1 times Tz over Tz, which is actually shown here, and then you can now take these two fractions together. In order to see the expression clearly as the gain and the zero and the poles, we can combine the terms which are in Z. So these are here, and this is just a constant. Now we can rewrite this further to get this expression. So we now recognize directly what the zero is here. We can go even further by divide out the t here, so we can now recognize also the pole directly. Now that's then shown here. So we divide the numerator and denominator by t. That's only this part. And we have now this expression. Now, if you now compare this to the general expression from here for the PD controller in the digital domain, you get now the K and the Z of C, which is our zero of the PD controller and the pole of the PD controller. Now, when you now compare the terms, we recognize the following. The zero must be this. So K2 over K1 times T plus K2. That's definitely correct. And we have also the K, which is here, which is this gain, which is then K1 plus K2 over T. And we also see that the PC, which is actually 0, so that we have a polarity origin in the Z-plane. So we move on. So we can say this transfer function for the PD controller is then given by this, so we can just replace this by the Z, which is exact same. So root locus equation, that is what we use for the design of our digital PD controller. This is the root locus equation, which is 1 plus the loop transfer function in the Z domain is equal to 0. And our loop transfer function is now the PD controller times the GZ. Now we have actually the expressions for both of them, except of course the parameters for the PD controller. This is now the expression. Now we need to determine now the KZ and also the K here in order to get that required transfer function for the PD controller. So the two unknowns, KC and the K. First, we start the angle condition. So for that, we need to look at the couple of phases, and this is already given as an expression here, and that comes from the poles, two poles here, 1, 0 here, and also the pole here, and also the 1, 0 here from the PD controller. So for that, we need to first draw in order to understand this clearly, we need to first draw the z-plane here, which is then the real and imaginary values here. So the imaginary axis and the real axis. So we have set the origin and also two poles, which are given here as the cross, and a 0 here. These are all given in blue, which is the planned poles and the 0. Now they're at these values. So you can see that also here in the expression. This is now the 0 and these are the poles. Okay, now what is then the required calculation here? Now we need to move towards the design point as we did in the root locus design for the analog controllers. So the ZM here has a real and imaginary value. Now the real value is 0.448 of the design point and the imaginary value is 0.409. And this is ZM. Now we will now relate the phase, in this case the first condition, towards this design point for these poles and zeros. So let's start. We start with the first pole, which is this one, and the second pole here, and the third one is the 0 here. And that will give you some phase contribution, phi 1, phi 2, and the phi 3. These are the phases here. Now, for each pole, you will get negative phase contribution. That's why we have a minus sign here, a minus sign here. And for the zeros, we'll get a positive phase contribution. That is the reason why we have a plus here. And the PD here must make sure that this expression on the left side must be equal to minus 180 degrees. And the PD controller has the 0 and the pole. Again, the 0 will be positive phase contribution and the pole will be a negative phase contribution. That's why we have a negative here, the minus. So let's then determine the phi 1 and phi 2, etc. Phi 1 is this angle. You can calculate that angle by calculating the angle here, which is a smaller angle. So you do 180 degrees minus this angle, and this angle is calculated by arctangent formula. So the height divided by this distance, which is shown here, and you will have now 93 degrees. The other one, similar, the phi 1, you can calculate phi 2 angle here as said before, and that will give you 111 degrees. Phi 3 is this angle, which is a smaller angle than 90 degrees, so we can directly use the arctangent formula, which is again the height divided by this distance. In this case, this distance here, 0.659 and plus 0.448. That's why we have it there, and it's then approximately 20 degrees. Okay, the formula was this for our angle condition. Now we have it here, we substitute now everything, and now phi PD is now 4 degrees. So our PD controller must contribute only 4 degrees. So what does it mean? It means the following. We need to first determine also the 0 phase contribution, the pole phase contribution of our PD controller. That's shown here. This is the phi PC. So how much is that? Now the phi PC is arctangent of this height divided by this length, which is just this 0.448. That is 42 degrees. Now, in order to see how much this 0 must contribute in this case, because the 0 location is not known yet, we need to again use this equation. That is a 4, that is a 42, so we need to have a phase for the 0 of 46 degrees in order to get that PD controller phase of 4 degrees exactly. Now, looking at the geometry, we can say this is a 46 degrees, which is a smaller value than 90 degrees, so between 0 and 90 degrees. So we can set up now the formula for the tangent, which is again the height divided by the distance here, which is not known. So that is the difference between this value and the value what's supposed to be here, which is then the z of c. So we can work this out and express the z of c, which is the location of the 0, in this format. And when you now substitute here the 46 degrees, which is determined, you will get here 0.053 as the 0 location, and that is shown here. And that is the phase contribution as shown here. Now we have the complete picture for our root locus diagram, and with all the poles and the zeros, including the poles here given in red for our PD controller, and the blues one are for the plant itself. So that means the following: our transfer function for the PD controller in the digital domain is now given here, and you know, in this case we only have the k as the unknown. So we move on with our root locus equation. We also already said this is it, and this is now the root locus equation again. Now we have this 0 here, so it has some extra. And now we can combine this, work it out, such that the k times some fraction is now recognized here. So we need to now use the magnitude condition as the second part of the root locus equation. Now the k is now expressed in the other parameter, so we place this 1 to the right side and then divide as follows. So we will get -1 divided by this coefficient in front of the k, and you will get this one. Now we need to substitute this design point, which is here in Zm, in this expression. So you can see the Zm, Zm, Zm. So everywhere where we see a Z, it is now replaced by the Zm. Now when you do the substitution, you will get this long formula. We can simplify this because you see here the real value, also the real value here. You see the real value here, also real value here. So you can now combine them together to get the effective real value. The imaginary value won't change because there is no imaginary value here for our other values here. So we get now this expression. Now we need to take the magnitude of this, so we need to see how large that is. And that is using the formula here, so the square root of the real and the imaginary values, and then multiply that together. This is just a number, so you don't have to bother about that. Just use it in your denominator. And when you do the calculations here correctly, you will get 3.895 as the gain. And that is the gain we require for our PD controller. That means the complete PD controller is now given here. So the gain and the 0 location. Now we will now use this in our closed loop transfer function and see if this is performing as we have expected for our specifications. So let's first look at that, but before we do that, we'd like to know what the MATLAB script I have used for my simulations. Now this is the digital PD controller designed by me, and the script here. This is the S parameter definition, this is the Z parameter definition in MATLAB. This is the plant, which is shown here, again as we have there. And this is the sampling period, which is the parameter. And this command is important, which is continuous to discrete time transformation. So it is the G of Z, which says it has now the first entry, it is the GP, which is our Planck transfer function. The second entry is our sampling period, and the method how we convert that to the digital domain. This is the 0 order hold. Okay, that's also what we have used, because this hold operation is a very simple operation. So it samples and then holds that horizontally. You can also do first order hold, that goes then holding and then goes linearly up to the next sampling. And the K value for our controller was 3.895, and the 0 was 0.053. So, and this was the formula, so you can just use this formula directly, and this is also shown here. So, and this last command is to get the closed loop transfer function. It's the feedback command. This is the forward transfer, so these two together. So this is what you see here. You need to put it in the first entry. The second entry is 1. That's just the unit gain feedback. And the -1 is because we have a negative feedback here. That's the closed loop transfer function. Okay, moving on to the simulation results. This is the first result from our designed controller. As said, this is the design point. This is the left side. This is the root locus plot. You see the unit circle here, and this is the blue one, which is our root locus diagram. The right side is our unit step response. Let's first look at the design point here, the current location of these closed loop poles, which is 0.451, and the imaginary value is 0.41. And we have here 0.448 plus J 0.409. So very close to what we have actually estimated or calculated. So this is a very nice result. But looking at now the unit step response, we see the following: the settling time and the overshoot. The performance is shown here. That is 0.329 seconds for the settling time, which is smaller than 0.4, so that is fine. But the overshoot is 12.3% here, which is larger than 12%, a little bit larger, but still larger. So we can say this is fine, but this is not fine. So we need to lower this limit. So we can adjust this controller. We can adjust the parameter, which is the gain here, or the zero location. So we have two knobs we can tune here. So we need to tune that. So the next step is tuned controller. I just tuned that in the MATLAB. I actually changed the gain. The current location of this second order poles are still very close to what we have here. So we can read here 0.452 and 0.408i, which is also very close to what we have. But the unit step response shows now exactly 12% and also 0.33 seconds. So these are the performances, and we can say exactly as what we wanted. Of course, you can move on by tuning the parameters here and then get a lower overshoot, maybe a lower settling time, or maybe both. That's still possible. This is where I stopped actually of the tuning, but you can get it maybe better. Alright guys, this is our example number 3 about the digital controller design. In this case, we have discussed the PD controller. We have determined our design, put in the S domain, then converted that to the Z domain, and we then worked out the required parameters for the controller using the root-locus equation. And then tuned the controller just again here slightly to get the overshoot limit down to specifically 12%. If you have any questions, comments about this example, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thank you for your cooperation and see you next time in another video. Take care.